come to the Vintage Computer Festival at the Enter Museum to see the evolution of From the Hole to the Cloud.
So please welcome Javier Alvarez for his presentation about the Playdate console and how he ported or developed his own Game Boy emulator for this little console. And as a little gimmick, he is also running his slides directly on this console. So please welcome Javier and enjoy the presentation.
Thank you for the introduction. So yeah, this is a date with a Game Boy. It's going to be kind of a story of how I went from, getting a Playdate to actually wanting to play Game Boy games on it, and then getting nerd sniped into actually implementing an emulator into it. So just a quick recap of who I am. I'm Javier Alvarez. I'm Spanish. I'm 32 years old, and I am a software engineer. And I basically like programming and electronics and music as well. And if you want to see my open stuff in GitHub, then you can just scan that. So let's go with what is a Playdate first. So the Playdate is a new handheld console that was developed by Panic in collaboration with Teenage Engineering for the hardware side. It's quite retro in the sense that it has a black and white screen. It looks very, or it has a crank, and the games are kind of released in a seasonal schedule. So you get 2 games per week for 12 weeks from the moment you get it, like from the moment you set it up. And then I actually got the revision B, so there have been multiple hardware revisions, and they actually have some slight hardware differences. This one has an STM32H7 B0 microcontroller on it with a Cortex M7 CPU running at 168 MHz. The display is around 240 by 400 pixels. It's purely black and white, so any shades of gray that you want to display actually have to be done with dithering. It has 6 megabytes of DRAM, so that's all the available space for your game. And you have 4 gigabytes of internal storage. So the 16 megabytes of DRAM will be actually very useful for the Game Boy games, because some of them were actually quite large. So, I mean, you get it, and it kind of looks like a Game Boy, right? When I got it, I just thought, you know what, it would be really, really cool if I could actually play my old Game Boy games from when I was a kid. Because it basically has all the features of the Game Boy. I just don't have to carry it with me, and at the same time, you also get a highly reflective screen, because the Game Boy display wasn't that great back then. So I thought, well, I will look up for already some emulators that run on the Playdate, and there was actually one, which was called Playboy, quite an appropriate name, to be honest. So I went ahead, tried it out. This was publicly available in GitHub, so yeah, that was great. Except that then I tried it, and it ran at about 1 FPS per second, so like pretty slow. And I thought, you know, I could actually go and improve this one, and that would probably be faster. But yeah, I have too much time, I guess. So I decided to actually write my own. And that's how it's when I started looking in, okay, how do you actually program the Playdate, right? There's like 2 main APIs that you can use for the development of the Playdate. One is a Lua API, which is really featureful. It's quite simple to write. You have a garbage collector, so it's just generally really simple to work with. But it's not really very suitable for an emulator, because of the garbage collector on one hand, and just because it's not as performant as a native C API. So the native API allows you to define an event handler entry point. In this event handler entry point, you get some events like initialization, when the player goes into sleep, out of sleep, so all the lifecycle management of the game. And then you can also set an update callback. So with this update callback, then you can get a callback every time that there's a frame update. You do your work, you update the screen, and then that gets displayed. And then to communicate with or to actually perform work on the playdate, you need to use a set of APIs. The way this is handled in the playdate is actually quite nice, I believe, because it has backwards compatibility kind of integrated into the system. They provide you with a set of structures that they can extend, but they won't break compatibility with. So you maybe get more members in the structure, but that's about it. And they are basically function pointers to the different things that they can do. So you don't need to, when you build a game, you don't need to care about relocations or stuff like this. That's kind of nice. So okay, I thought I'll go with the C API. But then it's like, yeah, I mean, that's fine, but I kind of want to have nicer development experience than just writing plain C. So yeah, that's when I actually found this Crankstar project, which is, well, as they describe it, it's actually on their webpage, a widely incomplete set of bindings for the playdate. I found that not to be that true, to be honest. It's actually served my purpose pretty well, and then I could actually program in Rust for the game. So yeah, that's how Rusty Boy was born. Yeah, so okay, now we have kind of selected like the language environment that we're going to be working in, and we need to actually see how the game works before we start implementing anything, right? So the first thing is it has a CPU, which is a Sharp SM83, running at 4.19 megahertz. This CPU is kind of a weird mixture between an 8080 processor and a C80 processor, but it has its own extensions and it's not really compatible with either of them. But okay, it's actually a decent CPU. And in terms of peripherals, you do have a pixel processing unit, which is the one that takes care of drawing the pixels on the display output. That has 8 kilobytes of VRAM to perform the drawing of all the video outputs, which, yeah, would not be enough for the size of the display, except that they actually use tiling, as most of these consoles. And the display is 160 by 144, so it's a bit smaller than the playdate display, and it also has a bit of a different form factor, but interestingly it has a bit depth of view, so you can display 4 shades of gray, which we cannot really do on the playdate, but we'll figure it out. We do have a joypad input, a timer, some DMA for automatic transfers between memory regions of the Game Boy, a serial port for the link cable, so the cable that allows you to communicate between Game Boys and like exchange Pokemons and this stuff. And an APU, which is the audio processing unit, with 4 channels. Like 2 of them were square waves, 1 of them was a custom wave that you could program, and a noise channel. The cartridges, interestingly, are extensions of the hardware console, so you would actually plug the cartridge into the CPU bus, and then you would just get more ROM or more RAM or new peripherals. So that's why you have some of the games that, or most of the games, they contain mappers that you actually also have to emulate. And they can have things like a real-time clock or a battery backtest RAM, or you can do like bank switching also to get just more memory that you can address, right? And actually, you do need that extra bank switching because this Game Boy is just 64 kilobytes of address space, so it has a 16-bit address bus. But as you can see, like the first 2 slots of 16 kilobytes are reserved for the ROM. The first bank is always fixed to bank 0, but then bank 1 is switchable between 1 and n, depending on the kind of cartridge. You have some amount of video RAM that is used by the PPU, as I said before. Then you have more RAM that can live on the cartridge. I draw it there, just 8 kilobytes, but in practice that is also possible to bank it, so you can have lots more RAM. And then for the games that were actually really simple, you don't really need to have or put RAM on the cartridges. You could just use this working RAM area instead. And then on the bottom row, you can actually see some of the I/O registers and other more specific purpose memory that we'll go into later. So in a nutshell, what an emulator kind of looks like is this. You have a step function which you run a single cycle, well, not a single cycle, a single instruction of the CPU, and then you advance every peripheral for that number of cycles that you executed. This will actually depend on how long the instruction takes to execute. If you wanted to, you would actually go in one level deeper and literally move every cycle, every peripheral. But this one is simpler to implement and hopefully more performant. It's actually important that you run it this way to be cycle accurate, so that the PPU actually draws the contents of what's really being populated by the game and not something else. Because the CPU is the one that is actually going to be line by line changing the contents of what's getting drawn. So we are executing the CPU, then we execute the PPU, get whether there was a PPU frame output or not. And then just step the timer, the DMA engine, and if any IRQs were triggered, we just notify so that they get handled in the next step. Let's go a bit into the CPU now. We have basically a registers of an 8080 processor. You have the two kind of access to the registers. One is individual register accesses for A, B, C, D, E, L, H, L. But you also can use register pairs, so like AF, BC, and so on. And then you have the two purpose-specific registers, the stack pointer and the program counter. In terms of instructions, it's, as I said, very similar to the 8080 processor. So it has actually around 500 instructions, more than the 8080, but and some of them are kind of unique to playdate. But in general, you have load store, arithmetic, bitwise logical operations, stack operations, control flow operations, and just regular bit operations like rotating, shifting, and like checking whether a bit is set or not, or stuff like this. So for our emulator, we actually have to go through this and implement all of them. And on top of that, each of them has actually different addressing modes, right? So you maybe have an instruction that is just moving some immediate value into a register that would use the immediate addressing mode for single bytes, but it could also be targeting a double register, so it would be a word, right? So 2 bytes. You could actually do immediate indirect accesses to write something or read something from a specific memory address that's coded in your program. You could use register accesses as well to target a register as a source or destination of the operation, or use an indirect register access to use the value in the register to access the memory. So this is kind of how it would look like. You would create an enumeration. You can think of this as an union in C, but it can have contents inside, and it's differentiated. So you have all the addressing modes that we just talked about, including like the register pairs, registers, and everything that they would actually need to execute. And then on top of this, we can create a set of opcodes, which are more generalized instructions. So like, for instance, this LD8 opcode is a load 8 operation from some source mode, from some addressing mode to some destination addressing mode. So for instance, this could be a simple move between 2 registers, like a load 8 from register B to register A. Or it could be something more complex, like loading a value from an indirect register access to a register value. So you would basically repeat this for all of the operations. It's a kind of a tedious process, to be honest. And then at some point you actually have to go from the raw bytes and figure out which one of these opcodes is the one that you're trying to do, right? That's the decoding process. In the decoding process, you could create a decoder table, and in this decoding table, you would go through all of the possible 256 opcodes or instruction codes, and then create the associated opcode representation in Rust. That's kind of painful, so what I did instead is I had a macro that would allow me to perform pattern substitution in the bit patterns. like you see here. So for instance, the lowercase r is a variable of type register, which has an enumeration of 7 values, and they just get replaced there. So basically it makes my life easier and makes sure that I'm not making a mistake, making a stupid mistake. Okay, then the coding is basically just indexing that table. So that's all you need to do. Except if the instruction is a prefix instruction. So because there are 500 instructions, one of the instructions, one of the opcodes is a prefix opcode, which then tells you to read the next opcode and interpret it differently. So if you get that first from the first decode function, then you code decode prefixed and then get a real opcode. And then executing instructions is basically taking the opcode that we just had and using it to do our work. So that would basically be for, I put here the example of the load 8, which would be taking 8 bits from memory at the addressing mode that we had as a source, and then putting them in the destination addressing mode. The nice thing about this is you can kind of encapsulate how the addressing mode happens behind the scenes, and then have a common way of handling all of them. So you will actually have a huge table here, so you can say like a switch case statement here with all of the possible opcodes and all of the possible combinations for every single instruction. And that brings me to the point of testing, because that's going to have bugs, whether you want it or not. So I kind of came up with a strategy that would allow me to define the test cases in just a declarative way without actually writing code. And instead what I write is a configuration file that tells you the input status of the CPU, a program to execute, the number of cycles that you're going to run it for, and then the exit state. If that exit state matches the actual exit state of the CPU after running the program, then the test passes. It's pretty simple. There's 2 examples here. One is just a move between 2 registers. So you can see if in the initial entry state, the value of the A register is 0, and then D is 130. And then the output status, the output state of the CPU should be just that the A register contains 130, right? And we have moved the PC by 1, yeah. And the one at the bottom is a bit of a more complex one, where we're actually writing to memory at address 1, 2, 3, 4, which is the values of H and L, the H and L registers. Okay, that's the CPU. Now let's focus on the PPU. So the PPU is actually organized, or what you're seeing here really is what the PPU is supposed to do, okay? You have a background which uses one tile map to draw to draw itself, and then you can put a window on top of it at some location marked by these 2 registers, WX and WY. And on top of that, you can have sprites, and the sprites are called objects in the Game Boy. So you can just position them wherever. They also use the tiling mechanism, and you just draw them there. So, if you have a look at the contents of the video RAM of the PPU, you basically see the following. You have 2 tile maps and then 3 tile blocks. The tile blocks are the definitions of what the contents of a tile are. So an 8x8 array of pixels that contain basically what the graphics of the tile. In actuality, it's not really the pixel values, but what you get is a palette index, and then you use the palette index to transform that to a real pixel value. But that's kind of another implementation detail. And then you need to know which tiles to actually draw, because basically the tile blocks are just collection of tiles, but they are unordered, they don't have any meaning there, right? The tile maps are the ones that determine which ones you're going to draw for the background or which ones you're going to be drawing for the window. These are 32 by 32, so in total, if you do the math, it's around 256 pixels by 256 pixels. The reason why it's larger than the Game Boy size itself, like the 160 by 144, is that it's also used for scrolling. So you could actually move the index of where the background is started to be drawn in the tile map and perform scrolling this way. That saves you basically from redrawing everything every single time. Yeah. So if we represent this in our code, it basically is coming up with data structures. We can represent a single tile line as a combination of 8 pixels, and these pixels are 2-bit depth, so 2 bytes. Then the tile is a combination of 8 lines. The tile block would be a combination of 128 tiles. We will have 3 of those. A tile index is a single byte. Actually, this index is then used to either index on tile block 1 and 2 or tile block 0 and 1, depending on the value of the bit 4 of the LCD register. So this allows you to also have a different set of tiles for the background or the window or the objects. And then we have a tile map, which is just a combination of 32 by 32 tile indexes. So our VRAM is basically just a combination of the 3 tile blocks and the 2 tile maps. And that's supposed to be just exactly 8 kilobytes of RAM. Then we have the objects, which are not stored in the VRAM. They are stored in a second region of memory called the Object Attribute Memory, the OAM, and it's 160 bytes in size. In here you have up to 40 different objects that can be drawn. You give them, they have a location, XY. They have the tile index that they need to draw, so what object they're going to be drawing, and some attributes like flipping the objects in X or Y. Yeah. So the way that the Game Boy or the PPU is actually drawing the pixels is through a continuous frame, and actually many games take advantage of this fact, because the PPU draws line by line. It means that the game can just move, be slightly ahead and be drawing the content of the next line before it is drawn. So that's why you need to actually be cycle accurate. There's 3 modes. This is the first mode is the OAM scan. And so we scan the object attribute memory to find up to 10 objects that we're going to draw to the line. Then we actually go to drawing pixels mode 3, which draws a single line. And then we go to horizontal planking. That's just basically a weight. And in there, in horizontal planking, the CPU can update VRAM or OAM if needed. Then, once all the lines are done, you go to the vertical planking, where the CPU can also prepare for doing the game logic until the next frame is displayed. So for us, implementing this kind of means having a step function in which we take a number of cycles to execute. We see if we just change modes, right? If we change to the OAM scan mode, then we actually run the OAM scan process, which is just filtering the 10 objects that are present in the current line, or up to 10, there may be none. Then when we go to drawing pixels mode, we just draw the line. This sounds simple, but it actually implies going through all the data structures to find the right thing. So it's a bit involved. And then when you hit triplank, you have full frame. So at that point, you can actually take the thing that you've been drawing and put into the screen. Yeah. Some remarks about the PPU is that choosing the right data structures is actually about 90% of the work. If you have the right data structures, you can then really easily implement this. And especially in Rust, if you use iterators, that's happened to be really, really simple for me. But it's true that there are quite a few edge cases of how the things are drawn in the display. So they probably could be considered bugs in the original design of the Game Boy, but nowadays you have to emulate them because it's the behavior of the Game Boy. So it's highly recommended that you try against the DMG AC2, which is a game test that you can run, and if you get the pixel by pixel the same correct value, then you know that your PPU works at least correctly for the edge cases that are tested by it. Ideally, we try to cache as much information as possible between lines or processing of the lines. This is kind of important also because the playdate is running from DRAM, and a lot of the time we are doing very random memory accesses, which is not great for the performance. We still need some dithering algorithm to upscale from 160 by 144 to 266 by 240 on the playdate. So the current progress of the emulator is it emulates all Game Boy peripherals except for the APU and the link cable. I should also mention that it's actually only DMG games, so no Game Boy Color games or Game Boy like Advance or whatever, only the DMG Game Boy. It supports 4 mappers, which actually cover most of the games that I have, if not all of them, I think. And it has a decent performance basically, so somewhere between 70 and 100% depending on the game and the workload. Yeah, let's just go to a demo. So right now, I'm gonna go out of the slides. I'm just going to go into my site loaded, here's Rusty dates, and let's pick, I don't know, Pokemon. Sorry, because you will actually see some Spanish in here, so it's just my game. But I hope you don't mind. Basically, here you have your Pikachu running in front of you. Yeah, so I'm going to skip this. So interestingly, this is one of the games that has an MVC5 cartridge, which means that it has a battery backed SRAM that it uses for saving the game state. So because I'm also emulating that, I can actually continue my previous game. And now I'm here right where I was. I can go around and play, or talk to Pikachu and see how it's going. And then Pikachu seems a bit sad. But that's rough. Yeah, so that's really it. I mean, that's all I wanted to show for this demo, really. You can come up later and play if you want. And let's just go back to the slides for now. Good. So I just want to take a couple minutes talking about performance and how I kind of went into improving the performance. The first thing you have to do is try to approach this in a systematic way. So I first identify what hotspots are in the program, what can you do to get rid of those hotspots without sacrificing any accuracy. And if you have to sacrifice some accuracy, then well, what can you do? So for the first part, you can do a coarse analysis of the target, running flame graphs. So by building this on Rust, it also means that I can have an SDL backend, just like you guys did. So it's actually quite helpful for identifying and running things on your host computer without having anything else. You can examine what's worth optimizing, explore any optimization possibilities in those areas, and then you can test improvements. One specific case of this is the player runs at up to 50 Hertz by default, but really starts at 30 Hertz, or the default is 30 Hertz, but can go up to 50. The Game Boy really works up to 60 Hertz, so yeah, we have a mismatch, right? I could run 50 Hertz, but that wouldn't be great, because then the games would run slower, or I could run 30 Hertz and just roll 1 every 2 frames. So I want to with the second option, and then that also means that I don't actually have to execute one of the PPU, the pixel processing unit, for one of those frames. So I can save all that work. Then a second one is, what if you sacrifice just a slight bit of accuracy, right? So if you remember in the very first step function that we had for our emulator, the very top level function, we were doing some work and then calling the PPU, the timer, the DMA, and all the peripherals, every single instruction of the CPU. This turns out to be quite wasteful, because you're doing lots of checks that most of the time you don't end up doing anything. So you can actually get away with only calling it around every 60 cycles, and then the games don't really suffer in performance. Yeah, and that's it for the talk. If you have any questions, I would be glad to answer them.
You have questions? We come with the microphone to you.
Yeah, so actually I have 2 questions. The first would be, how did you manage to run a presentation on the thing?
Okay, so I mentioned that there are two APIs for the Playdate, right? One of them is a Lua API. It turns out that building a game for the Playdate is really trivial. So building a slides is basically building a game.
Okay. Yeah. And my other question is, could you potentially also do something with the emulator that you could sort of program like the crank in to do like specific functions in specific games, or is it not?
I mean, yeah, you probably could. I just didn't go with it because it's not the default behavior of a Game Boy, right? So it probably would work fine for some games, but not great for others.
Oh, yeah.
Right?
Like in a specific case, maybe you could.
Yeah.
Okay.
Yeah.
Okay.
More questions?
Sure. Any experiments with the APU?
Wait, please, for the recording.
Just any experiments with the APU? How the performance? Or?
Right. That's a really good question. I haven't actually done the work of implementing the PPU so far. The main reason for that is because I'm often dropping from 30 FPS. So that would mean that I would then drop audio frames, and that would be pretty awful. So I hope to actually improve the performance a bit more, and then I can maybe tackle the PPU.
More questions? Don't hesitate.
Thanks for the presentation. It's cool. I would like to hear a little bit more details about the dithering.
Right, yes.
Yeah, I think that it's also a tough topic, right?
Yes, it's a bit of a tough topic. I went with a very simple algorithm for that, actually, which basically looks whether the pixel that you're drawing is odd or not, and then treats the shades of gray differently. So I wanted to go with something really, really simple because it actually takes quite a while to take the frame once drawn from the Game Boy and then put it into the display. So for this process, I'm just looking at whether the pixel is odd in X and Y, and then if let's say it's a dark gray pixel, then the odd pixels are drawn black. Otherwise, for the light gray pixels, they are drawn white.
It means that the dithering is global, right? For the whole screen. So
yes.
It doesn't follow the objects.
It doesn't follow the objects, and that's why you will see actually if you look at the Game Boy games, you will see that there are some artifacts which are not great, but to be honest, I don't really know how to fix. If you had some suggestions, it would be great, because I just don't know. But like, you can see some artifacts here as well, right?
What about temporal aliasing? Like using the 20 Hz that you are not using on the screen?
Sorry, what's that?
Like a temporal aliasing, no? To do the switch quickly between gray and white in the 20 Hz that we're not using.
It is, I mean, this is actually handled frame by frame anyways, so...
But analysis is passionable. You are basically
yes.
trying to see it, no?
Yes,
I
yes.
mean, like quickly toggle in one frame put it black, in the next frame put it white.
I see what I mean. Yeah, that could actually work, I think, but the problem with that is actually there's a good example in the Playdate docs that shows you the alternating between two checkboards on opposite pixels, and that is really, really discomforting to the eye. So I don't think it would be a great idea. I mean, I could try it out. Maybe it's a good idea. Yeah. But I didn't consider it because of that. Actually, they also tell you to keep the same dithering pattern constant so that when you move around, it doesn't shift and cause this problem either. Which, yeah.
So I was gonna ask, did you make the game?
The console?
Yeah, did you make it or did you buy it and then program your own game on it?
The console is bought from Panic, so they do the hardware. They actually give you the infrastructure software so that you can put your games on it. And then what I did is put a Game Boy emulator on it, something that can interpret the old games on the Game Boy and just run them.
So it's like a scratch program.
Yeah, it's like a program from scratch.
Yeah, you also mentioned that the screens are similar and different. What do you mean by that? I remember that on Playdate there is no backlight on the screen, but was the same for Game Boy?
Yeah, the Game Boy also had no backlight. It's the difference. The main difference is that it had four shades of gray.
Yeah.
But it was also black and white. Although to be fair, it looked more greenish. So four shades of green, I guess. And what I meant by similar is the comparable sizes and maybe also comparable colors.
Yeah. And personally, what do you like more, the screen on Playdate, the screen on a Game Boy, or emulator, simulator?
I mean, if you have the emulator, it's probably better. The Playdate actually, I think, so the thing with the dithering pattern is if you look up close, it looks pretty bad. If you look at it from a distance, like from the console to your hands, it's not that bad, right?
Yeah,
so,
because my personal experience with the Playdate is that I really like how it looks on a Mac screen. I mean, it's a simulator, but when I take the actual device, it's not that great. So that's why I was asking.
Yeah. I personally actually like the Playdate more than the simulator, but I guess that's a personal thing.
Something about the actual Playdate itself. So besides like this emulation project, what exactly can you do with it? Are there like games online that people made that you can just download onto the device?
Yes, so there's a store that you can access and then buy any games from it. You will have also like games from itch.io or anywhere else like GitHub or whatever that you can just put on it if you sideload them. You also get the seasonal schedule of the releases.
And these games are custom made for the Playdate, or?
Yes.
Okay.
A little bit of context here. So there are not many Playdates sold by the moment, but the catalog is really huge. So the ratio to the console to the catalog is really big on the Playdate. So I think that it's maybe the fastest growing catalog for this small device, for this like very niche device.
Okay, so not a lot of people have one, but the people that do have one really like it.
Yes, exactly. and people really like building for Playdate. So it's a really nice experience because the ecosystem that they provide is like the best in class.
Okay.
Yeah.
That's very true. I mean, I didn't mention it, but Playdate actually has even a profiler, so something that you will only find in normally in a computer, So that's really great development experience.
So thank you for your great presentation, and give applause. Come to the front and have some hands-on experience with it.
Yep.